Hi, Merrick.
Hey Mateo, how you doing?
Oh, keep on keeping on. Friday's the best day of the week, right?
Yeah. That's a great those are great bookshelves you have behind you.
Oh yeah, this is my work, and then I thought I'd bust out the old Mars for today.
Nice.
Folks who maybe don't have memorized the geography of Mars. So I've opened up the room here, and we have 11 attendees. It looked like we had 53 reservations, so I think folks will continue to um, come in as the time progresses. But we are recording, so if you come in late or you need to see the beginning of this, you'll see it on the recording that we post afterwards. I guess I wanted to see if maybe folks want to introduce themselves in the chat. A couple things that I'd be curious to get to know is your name and where you're from, how you found us, what about the project you might like, anything that you want to add to the chat just so we can get to know you a little better. I'm going to show some slides at the beginning, hopefully not take more than 20 minutes, and then we're going to leave lots of time for questions so that you can feel like you're engaging with us. And if you have any specific questions about the science or the project, we'd be more than happy to answer those all. Anything you want to add before we get started?
No, I'm gonna keep my eye on the chat and try to be active there as well. But yeah, for people that don't know me, I'm Eric Slipsky. I'm out at JPL, Jet Propulsion Laboratory in Pasadena, California. I am the project lead for the other Cloud Spotting on Mars project, which launched, geez, over 2 years ago now, which uses a different spacecraft and different type of observations than this one is, and it's kind of focused on different science too. But yeah, maybe you've attended one of those webinars, but I'd love to know if anybody's sort of participated in both or uh, yeah, how you found out about this one and any questions you have about Mars.
Awesome. And my name is Matteo Crismani. So I'm running the Cloud Spotting on Mars shapes that we'll be talking about today. Merrick and I actually went to grad school together, so we've been friends for quite some time. And I'm an assistant professor here at CSUSB. So the spacecraft that I work with, the one that you're going to see more about today, is this one here. This is the MAVEN spacecraft. And we're going to be talking about some of the results from the 10 years of observations. So just what we're uploading now in batches. And of course, thanks to all of you working on this project, we've been able to make it through 2 subject sets already. So we'll talk about some of the questions that folks have had, the progress of this project, and where it's headed in the future. Hi, Nancy. Hi, Mel. And hi, Simon. I just thought I'd shout you out here. Yeah, if you want to drop where you're from and how you got interested in the project, we'd love to hear from you. If there's no questions before we start, I'll just take it away. Okay, and let's hope that I'm sharing the right version of this screen.
Yeah, it looks good so far. Yeah,
Okay.
it looks like a PowerPoint.
Okay, and it's not the view that is for the speaker. Hopefully this is the view for the audience. And I'm hoping you can see my mouse because I'm going to be using that to point some stuff out here. So that's my name here, and I'll include some contact info at the end as well, or you can always contact us through Zooniverse if you have specific questions. Um, this is the Cloud Spotting on Mars Shapes project, and this is MAVEN in orbit. Down here, I mean, this is not an actual photo, of course, this is a computer mock-up of it in orbit, but down here is the instrument that we use. It's called the Imaging Ultraviolet Spectrograph, and we are looking at the atmosphere of Mars here. You may be very familiar with the craters and the mountains that are on Mars, but we're going to see that in much more detail today. First off, here's a quick summary of the status of the project. I screen grabbed this earlier today, and it's already inaccurate because we're getting more volunteers every minute, and we're getting more classifications every minute. Right now, we finished 2 subject sets already. We've completed 1,100 individual subjects. We started looking at high resolution images, the highest spatial resolution that we had. We wanted to start in a very cloudy season so that folks had something to look at. And we were mostly looking at the day side of the planet. And we'll talk about where we're headed from there. So the goals in the short term, Mars is a complex, the atmosphere is a complex system. The dust makes it warm, and so that helps to either create atmospheric motion, and that can be linked to whether or not there is water vapor in the atmosphere or whether it is condensing out in the form of ice. And while we measure the pressure at the surfaces with both rovers and with spacecraft, we don't really have a lot of measurements of the wind. And so on Earth, of course, we have weather stations, and you can go up to mountain tops, and there's weather balloons and everything else. So we have very good measurements of wind that help us understand how clouds form here on Earth. And our thought was, can we invert this process? Can we use clouds at Mars as sort of a stand-in for the Mars weather stations that we don't have? Can we understand the wind at Mars using information about the cloud's shape and about specific types of clouds? So here's where we started. We started with the super high resolution data set. So this is an example of an image that you may have seen already. And we can identify some features in here. You can see craters on the surface. This purple on the top is ozone, which we'll talk a lot about today. And then, of course, the star of the show is the clouds, the stuff that I really care the most about. And what I wanted to do by starting us off with this and introducing this is to sort of give you some familiarity as a user as to what type of clouds look like in the higher resolution before we kind of go towards more difficult data sets. And I'm also finding, with great feedback and talk, that folks are identifying new types of clouds. And so maybe that leads to, branches coming off of this project that will try to identify some of these new things that folks are finding. This is probably the most common resolution you've seen so far. This is called the high resolution mode. And this is an example from folks who have been chatting about this in talk as well. I thought this was a great example image because you can see things like the volcano down here. This is Olympus Mons. So this is the largest volcano in the solar system. And you can also see that because it sticks up so far into the atmosphere, you actually get less scattering. So that means that it looks less bright. It's not darker because it's hidden or something. It's actually, it appears darker here because there's less light. And so that means less scattering. Here you have another example. You have that ozone, that's that pink color, and it's really well mixed with the clouds. So we'll see a couple more examples because I think folks have been having some issues thinking about, well, are these pink swirls, are they ozone or cloud? And we'll kind of address that when we see some more examples. And I really like this version here. This is a really unique cloud. So the sun is off to the right, and this is sort of near the terminator. Remember that the terminator is the boundary between the day and the night. So if you were standing on this part of Mars, you would be at sunset. And so just before sunset here, we have these big, tall clouds. And I can tell that they're tall because you can see the shadows. So this is a really cool thing that it sort of popped up that folks have been noticing. So if you happen to see, say, clouds with the shadows, even if they don't have that specific form, be sure to mark them with other. And so that way we can go back through that and categorize them as something that might be a unique cloud type. We also find that there's, it's not super straightforward that maybe you're looking at a gravity wave in this part and a disk in a different part. Sometimes they overlap. And so this is a great example here where there may be some form of a gravity wave feature, and it's just sitting on top of general cloudiness. And I think if I click to the next one, yeah, you can see the geography underneath. So this is Olympus Mons, sorry. And if I click between these two, it could be that these gravity waves, oops, sorry, went too far. These gravity waves are being launched by this crater. So that's something that you might not just see right away. So for example, sometimes we see gravity waves, they're coming off of a mountain. And that would be like the most traditional way that we see them on Earth, but Earth doesn't have a lot of craters. And so maybe there isn't a good analogous form to Earth. So instead here, it's really helpful if you spot something like that and you look at the underlying geology, you may be able to find the reason why these things are forming. Okay, so this is one example. We're going to go through a couple different examples, and then we'll talk about where we're headed.
Hey, Mateo, can I ask a question?
Yeah, go for it.
Yeah, I think that's a really cool point about the craters, potentially launching them, but also being correlated, I guess, with where you see certain types of clouds. Um, uh, is the best way to sort of mark those through talk, or um, yeah, is there a preferred way for something like this where it kind of takes both and
Yeah, so for
yeah.
this one here, like if you mark this as gravity waves, I think that's the right way. If you mark this one as other, I think that's the right way to do it. And then if you see something and you're not really sure, right? So for example, gravity waves don't have to come off of a volcano. What we're really interested in is is there structure in the clouds? Like, does it look like, and we're going to show some examples of this later on, where it looks less coherent. This one really looks like there are sort of like lines. So even if you see something like this, and maybe you don't even click over to the geology to look at what's underneath, that's totally okay. But if you do see something like this and you're interested in it and you want to chat about it on Talk, this is a great way to sort of draw my attention to it, and we can have a back and forth about what you might be seeing in the data. Oops.
Yeah, that's awesome. Yeah, I'm just gonna add because this is one thing we encountered a little bit. It's sometimes uh, not intuitive to go from the Zooniverse image you're seeing to to working with the image itself, or like making some notes on it. And just so everyone's aware, I'm pretty sure if you save or like favorite the image, you can go back to it and you can actually download the raw image, or even the different frames. And so if anybody wants to like kind of get deeper into a specific example where they saw something interesting, to bring it to Mateo's attention, you can download that image, open it in PowerPoint or Paint or Adobe or anything where you can kind of make notes on top of it. Um, Feel free to do that, and then it's a little hard to share, but either send it to Mateo directly or kind of in one of the talk boards, try to upload it. You may have to upload it to an image hosting site first. So there's like there's some barriers there, but if anyone's particularly interested in like, yeah, going deep into one, that's probably the best way to do it. And if you don't know how to get the images to us, just send an email.
Yeah, that's a great point too, Merrick, because I've certainly had some feedback about, folks who wanted to point something out on an image, and we can't see the markings. So if you make something and you submit it and then you have a question on it right after, unfortunately, we don't get access to those until we download the data and sort of analyze it in bulk. So you may think, oh, I made all these great markings, and then what do you think about it? Or you want to ask our opinion on it, but unfortunately, we can't see them. So if you have a specific question and you want to like save that, like Merrick was talking about, and then send it to us, I'd be more than happy to chat that way. Or I've seen some folks who, treat the circle like a clock. And so they'll say something like, well, this is at like 4 o'clock. Is there something down there at 4 o'clock towards the edge versus, is there something towards maybe 8:30 halfway towards the center. And that's also a great way to kind of navigate on the globe if you can't make those pictures or you don't want to take that extra step in case you're interested. Okay, ongoing. So this one here, oh, we just did that one, sorry. This one here, like I mentioned, you have a lot of these overlapping features, and I got sent this one and I was just blown away because it really looks like it has everything that we've been talking about so far. So for example, we got disks, and you can see those disks right on top of these volcanoes. That's Olympus Mons again. These these four volcanoes create something called the Tharsis region of Mars. And this is a region where there used to be a super plume of volcanic activity. And what it would do is just like these volcanoes are enormous. And when I say enormous, Olympus Mons is roughly the size of Arizona. And it's so big, right? I told you that it sticks out into the atmosphere. It's about 20 kilometers tall. So it's so wide that if you stood at the top and you looked around, you wouldn't even notice that you were on the top of a mountain because it's so wide like this, right? It's not like when you think of, say, a volcano at Hawaii, or you think about a volcano like the Mount St. Helens that are very well peaked. These ones are very wide, and so we can see them from space in a lot of detail. And of course, in that same process, you get these really beautiful disk clouds that form around them. So this image is a great example of them forming, but they're not so simple as to just form disks. Sometimes they have gravity waves on top of them. So here you can see this structure that has formed on top of the disk, right? And similarly over here, someone pointed out that this really looks like it's curling, and I could certainly see that. If you said to me that's a vortex and someone else also said that wasn't a vortex, I wouldn't tell either of them that they were wrong, because I think that it certainly could be in the way that it's curling around. And on top of that, you have this beautiful structure, right? So this is that dotted cloud structure that's sometimes a little more rare than, say, the caps, where you have dotted clouds basically form because warm, moist air rises, and then as it rises, it cools. And what happens is that cooling will create a little cloud cap, but then there's still warm, moist air punching up from below, and it pushes it off to the side. And then when it sinks, it's cool. And so you have clouds, and then you have the absence of clouds. And so that essentially will look like these little dots all over the surface. And so we see on the edge of this large cloud feature, this is like how it's forming. This is the moist lower air from the lower part of the atmosphere rising up into the atmosphere, cooling and forming these clouds. And so this whole region in here, is not just a vortex cloud, it's also dotted on top of that. There might even be a streak up here. It's a little hard to tell when I look towards the edge of the planet because I don't have a lot of context for there. You also have in here, you have Vias Marineris. If I click between the underlying geology right here, you'll see this is the largest canyon in the solar system. So Mars got two. It has the largest volcano and the largest canyon. And this one here is so deep for the same reason that we talked about not being able to see, like it looks dark up here, not being able to see a lot of brightness above the volcano. When you have something that's deep, you have additional air to scatter, and it ends up looking blue in these images. So we'll see some more examples of that later. Down here, you have a nice big polar cap. This is the southern pole. All of our images have the north oriented up and the south oriented down, but sometimes that kind of moves around as the spacecraft is moving around the planet and taking images at different locations. And so what you see here is you still have ozone around the cap. You might be saying to yourself, well, is that a cloud? And I can look here and I can say there definitely is an ice cap down there, but this is actually probably all ice. And we'll see some more examples of the ways in which surface ice and water ice clouds can look very similar. But some of the dead giveaways are here that you can see these craters. And when you can see those craters, you're probably looking at ice on the surface filling in the crater. So if I flick between these two, you'll notice, oops, well, I lost it there. These are those craters that are down there at the bottom, right? These two, and then these three. Oops, went too far. These two, and then these three. And this just shows one of the cool things about Mars is that you have the transport of ices from the pole into the atmosphere and then to the other pole. And this does that every year. So the caps actually grow and contract and grow and contract. And it looks like in this particular part of the year that the southern pole is actually quite extended. So you also see this wispy type of cloud. We did not identify this right away as a particular cloud that we're targeting, mostly because I don't think that we could right away use it to measure something specific. So for example, a cap or a disk cloud, one that forms over the top of a mountain, is due to the fact that winds are bringing warm air up and it cools up there. And then it forms this little cap above the mountain. So we can say something specifically about the winds. These ones here, they are certainly interesting. And I think if you want to start tagging them with other, you're more than welcome to. It'll just take a little bit for us to figure out what it is that they're trying to identify for us, right? Whereas something like this, these broader motions, they're really talking about, broad scale motions of the atmosphere. Okay, cool. Let's keep going. Let's see some more examples. This pink stuff here, we have another example of sometimes there's pink with structure in it. And, the question I get a lot is that a cloud? And I think maybe the cheap answer is that sometimes. So sometimes they're clouds and sometimes it's just the ozone, depending on one of the strange things about ozone. So ozone is a product of CO2 and water interacting in the atmosphere of Mars, and it forms at a number of different locations. So sometimes you see ozone above the cloud, and then sometimes you see the cloud above the ozone. And so you might be able to, in this region, you see all this structure that's in here and say, oh, that looks like gravity waves. Well, that might well be gravity waves in the clouds that are either above or below the ozone. In this circumstance, I'd probably say that the ozone is above this cloud because it's sort of coloring the whole northern hemisphere pink, right? So if you had something that was bright and white, like a cloud, and then you put a pink filter over it, that's the ozone coloring the cloud. But that's not always the case. So if you see, if you have some like questions or you want to show an example and talk, or you're confused, I'm always happy to answer, and I try to answer within about a day. We talked a little bit about Olympus Mons. That's right there. And sometimes you get something like, what's this weird thing? Is that a gravity wave or what is that? And so it's really helpful to go into the geometry. And you can kind of see, so this is very obvious. This is a lot less obvious. So here's a feature in the surface that we're going to see a couple times here that is sort of presenting some cool results, because you can see that it's dark here, right? It's kind of sticking up out into the atmosphere. And yet clouds are forming right on its edge. They're forming right here, right? And similarly, you say, well, that was a weird thing that was more over to the right. It's forming right off of this set of like ridges and mountains. It's forming right on the edge of that, and they form horizontally. So maybe this is a great example of some gravity waves that are hitting the edge or a mountain range and then forming waves as they go backwards, right?
Mateo, there's a couple questions in the chat.
Okay, yeah, go for it.
I answered one about sort of Hadley circulation on
Yeah.
Mars. Then this next one is about ozone. So why is it pink in these images, and what's the difference between Earth's ozone layer and Mars's ozone layer?
Great question. So one thing we got to remember here first is that these images are actually not in the visible. So if you were standing on the surface, it would not look like this to your eye, but it would look like this to your eye if you were a butterfly. So what this instrument is doing is it's using ultraviolet light. And we are taking the ultraviolet light and we're moving it over into the visible. So you could call that false coloring. But really what it's attempting to do here is sort of make the entire world of light accessible to our eyes and not just to the instrument. So for example, here, the reason why it ends up being pink is that the feature that ozone absorbs or emits light with happens to be in the part of our, red, green, blue that happens to fall in the pink. So we just mapped that over. And it turns out that, it's very nice for looking at clouds in this way. So clouds show up white because they kind of reflect all light equally, whereas dust tends to be a little bit more yellow, and that is very reminiscent of how dust actually ends up working in the visible. They're not super different for a lot of these large particles. The main difference here between, say, Earth's ozone layer and Mars's ozone layer has to do with the fact that the Earth's ozone layer, we live in an atmosphere, thankfully, that's dominated by nitrogen and oxygen. And there is carbon dioxide, but it's not the dominant part of the atmosphere. Whereas at Mars, it's something like 96%, maybe 98, I forget exactly, percent CO2. And so instead, what you end up having is at the Earth, we have an ozone layer that's actually quite robust. It exists throughout the entire planet and is due to the fact that water molecules and O2 molecules interact with ultraviolet light. Ultraviolet light really likes to break apart molecules. And when you do that, you end up maybe with an extra oxygen. And if you have, molecular oxygen, that's 2 oxygens, and you have an extra, they can hang out and they become ozone, which is O3, 3 oxygens, right? As opposed to at Mars, you have to have an interaction between water and CO2 in order to get that extra O3 by itself. Does that kind of help? That's a lot of chemistry, I know, but I'm happy also to chat about that after. Yeah.
Yeah, we'll wait and see if there's a follow-up question.
Okay.
There's another one. You're talking about the CO2 rich atmosphere. Is it correct that the greenhouse gas emissions that cause climate changing on Earth could actually be good for Mars in terms of like melting the caps and making it more habitable?
Yeah, certainly this must have been the case, right? So Mars is, it looks like it's a desert because it has this very red color, but it's actually farther from the sun, so it's colder. And despite that, we see evidence on the surface for running water to have existed in the past. And the only way that's possible is, one, if there was more atmosphere in the past, and two, if it was significantly warmer. So we think that probably both were true, right? We see evidence of dry lake beds. We see evidence of dry river beds. And we know that there must have been running water on the surface, but there isn't today. And so, of course, one of the things that MAVEN is studying is the escape of atmosphere to space. And one thing that folks are really interested in is, what were the greenhouse gases that made it so warm so that you could have liquid water on the surface? Because even if you had a nice big atmosphere, if it's too cold, then you don't get running water. So CO2 definitely played a role, but people also ask questions about whether or not there are other types of greenhouse gases that may have existed on Mars in the past. Onwards.
Maybe I'll just give one more comment
Yeah.
about that because yeah, this comes up a lot for this, the caps and warming for terraforming Mars. People like to
Yeah.
wonder about if we can, change the atmosphere of Mars to so that we could live there. And there have been studies that show that you could basically melt both polar caps, and you're not going to put enough you'll put a lot of CO2 in the atmosphere, but not enough to actually uh, warm it enough for it to be Earth-like.
Yeah. Yeah, that's a great point. And I think, human exploration on Mars is very interesting. And I think probably in the next, I don't want to put a time frame on it, but in the next 50 years, hopefully we'll have geologists on the surface grabbing some really cool rocks. But, are we going to have a Hotel 6 up there? I don't think so. Mostly because, it's not as comfortable as the Earth, right? So we have plenty of atmosphere here, and there's really not that many resources there for terraforming. You'd have to find a way to bring in asteroids and everything else, and it wouldn't be as fun. Okay, so we're going to keep an eye on this one. We're going to come back to it later. I think there's another great example of this region and how it can trip folks up. So here's another example of structure within the clouds. And this is that overlaying again of ozone on top of the cloud. And I think, someone dropped this in the chat and they're like, I think this is a swirl. And I'm beginning to believe that they're certainly right here, because look at the way that it's turning around. And this is these large swirls that we see, especially in the northern hemisphere. We have yet to see them as frequently in the southern hemisphere. Doesn't mean they don't exist. I haven't heard talk about it very much. You may be thinking to yourself, oh, that's a cloud too. But we can look at the underlying, oh, I didn't add this one here. Oh gosh. Well, if you look at the underlying geology, this is actually probably part of the cap. You just can't see the whole cap because it's sort of in darkness. But one of the cool things to note, one of the ways to kind of tell, you might see that there's kind of a dark ring around it. So that can be an or a thing to help you identify if it looks very cloudy and then there's a ring. It could be that is ice and then inside of the crater at the bottom is where the rest of the ice is, right? So it's always good to check the geology overlay so you can kind of tell what you might be looking at there. Whereas that is certainly a cloud in the vortex. Oh, you can kind of see it in here. This is the North Pole. You can see some of those lines in there. Okay, I think I said a lot about that. Let's go to the next one really quick, unless there's a question. Okay.
Nope, not at the moment.
Cool. So, oh, this was the example I wanted to show. Good. So here's another one. You can see this really bright dot, and you can see what looks like a really interesting cloud here. And of course, this one's going to break our heart as we flick between this one and the next one. We are actually looking right down on the pole. And this is the underlying geometry. So that crater that we saw earlier, boom, it's right there, right? And so you can see all of this surface ice. Now, interestingly enough, sometimes the northern cap doesn't seem to extend or retreat as much when you compare them to the images. That's just because whatever picture that we took these surface maps from happens to match what you're looking at, right? So sometimes they won't match, and that's because, and I'll show you in a second, you're looking at a different season. So during the southern winter, for example, the winter cap will get really big. And then as you get into southern spring, it starts to retreat. And by summer, it's at its smallest extent as most of it has evaporated. And then it'll start growing again as it gets colder, right? And the same is true in the northern hemisphere. So as you have transport of ice from one pole all the way across to the other and then back again. And that's a yearly endeavor. Here we also see this is that same gravity wave that was happening off that feature that I told you about. This is the one that looked like a little ridge. And so it looks like it's hitting the side of that ridge and then creating these wonderful little reverberations, like striking a string on a guitar. So if I flick back and forth that, you see the reverberations here. I'm not sure if I would call this a vortex. It's certainly cloudy. But if you wanted to like draw someone's attention to it, we could talk about it in the chat.
I have a
Okay.
question on the
Yeah.
this figure right here, or sorry, no, the surface.
Yeah.
How do I know if something's a crater or a volcano?
Yeah, very good question. Very good question. So this, for example, is a crater. And this, for example, is a volcano. And usually the only way to tell, unless you've memorized them all, right? So for example, if you're lucky, you have a little Mars, but of course not everyone has a Mars at their home office. And so what I'll tend to do is if it's very circular, if it's almost perfectly round, it's more than likely a crater. So craters are the result of really, really energetic impacts of comets or asteroids into the surface. And they explode with such force that they remove any remnant of the direction they came in. They burrow into the ground and then they explode in the force of several atomic bombs and they make a hole that's perfectly circular. So if I'm looking at the surface and I see all of these little dots, these look really circular. Whereas I compare it to this, and this kind of looks like it was sort of squished or stretched out. And that's going to be my first clue as to whether I'm looking at a crater or I'm looking at a volcano. The second one is going to be whether or not there is, this isn't a great example. So you have this little dot in between, and it looks like there is shadow on the left and light on the right. So that's the idea that this entire image is illuminated from the left. And I think most of our maps are that way. So they should all have the same illumination so that craters will be dark on the left and illuminated on the right. And you can kind of see that is consistent. We try to make it as consistent as possible. So here you see you're looking at it from the other direction. So you're looking on the wrong side of the planet. Remember, this is the North Pole right here. And if you were to tilt your head and imagine you're looking down at this part, it would be dark on the left and bright on the right. So let me show you another example. We can go back and I can show you that again. So dark on the left, bright on the right. Whereas here, when you were going up in the mountain, Olympus Mons goes up, then we have light on the left and dark on the right. And this is sort of just the convention of seeing whether we're looking down or we're looking up. And if we go even farther back, let's look at this is a canyon system. So we're looking down into the canyon. Oh, sorry. With fat fingers here. So again, you have light on the left and dark on the right. And similarly, you can kind of see how it would be illuminated going down on the left. See how it's down on the left? And then if you look down into this crater, it's illuminated here, down on the left, and dark on the left and up on the right, light on the right. Does that make sense? I don't know if that was helpful.
Yeah, I think that's helpful, and it's something to if people are interested to just always kind of be looking at and questioning yourself of what's what, and think about where the light's coming from, and if something's like this or like this.
Yeah, yeah.
Yeah, yeah, go ahead.
No, and we try to be as consistent as possible. So if you have a question, you can always drop it in the chat, and we can try and answer it as quickly as possible.
A couple questions. One, I think we should do right now, which is why do we use the term gravity wave for what appears to be phenomena created by topographical features?
Yeah, that's a very good question. So gravity wave, it got very popular when folks were talking about two black holes merging, right? But it actually is a much older phrase, and it comes from the idea of what happens to a blob of air that you heat up. So as you heat up a blob of air, it becomes less dense than the surrounding air, and that pushes it up, right? And so if you keep doing that, sometimes you can get it to go all the way to the top of the fluid. And so you might, for example, you might make soup tonight at home, and you have the heat on the bottom that is warming up the gas or the fluid, and that rises and it makes bubbles. That's called convection. But you can have a different situation where instead of it continuing to rise, it might overshoot the place that it wanted to end up at. And now it's actually heavier than its surroundings, and it comes back down. And so it can overshoot that place again, and now it's lighter than its surrounding, and it goes back up. And so it's going to bounce back and forth like a pendulum, and that is due to gravity. So this is sort of an older terminology that's associated with how fluids can sort of oscillate and bounce due to the fact that they're either more or less dense than their surroundings. And so that sort of is the reason why we talk about gravity is, so you might have, for example, a mountain, you go up the mountain, and as you come down on the other side, you might have that oscillation happening on the windward side of it. And those oscillations are due to the density changing as a function. Maybe we call them density waves. I don't know. That's a very good question. I didn't get to name them, so.
Yeah, very different from the astrophysics gravity waves. Okay, just to keep tabs here. Yeah, another question is about how you're actually going to be using the output data, for instance, for like wind or meteorology. And maybe that's something you're going to get to in a little bit.
Yeah. So for example, so we can do the simple ones first. The simple ones first are things like a streak cloud. And if you see a streak cloud, that usually means that you have a cloud forming, and that's telling you the wind direction. And that is a form of, you can use that to inform the wind. And of course, modelers who are interested in this can use that to see if their models can reproduce this phenomenon where we see it. So for example, if they can't produce any streaks in their model, that might mean that the wind that they put into the model is too chaotic, right? Maybe it has too much crossing back and forth that you don't get these nice long columns of of clouds. Similarly, the direction of a gravity wave can be inferred by the location of those streets. So if you have light, dark, light, dark, light, dark, then the direction of the wind must be in that same variation, right? As opposed to along it. So we don't have gravity waves that go sideways like this with the wind. We have them go perpendicular to the wind. So light, dark, light, dark, and the wind direction is there. So that immediately gives us some information about the wind measurements, and we can use those to ask, you know, both models and theorists of the atmosphere as a whole, whether or not they can reproduce where these cloud features actually show up. Does that kind of help? We'll talk about that definitely more when we get to the next stage as well. Those are the simple examples. We have harder examples as well.
Yeah, and there's another, I think this question is great. I'm kind of responding to it right now, but are there online books or documents to help with identifying these types of clouds? The field guide is useful, but it'd be, you know, nice to get deeper explanations.
Yeah.
So maybe I'll just tag that as something we should do. I know there's some papers for Mars for kind of what the different types of Mars clouds are.
Yeah.
Yeah, maybe that's something we should look into.
So
Kind
I'm
of
going to plug,
making, yeah.
I'm going to plug cloud spotting on Earth. So this is something that you don't need Zooniverse to do. You can go outside and do it. And I'm going to jump around really quickly and just, you know, jump to the very end. And for folks who might be interested, I always recommend the Cloud Appreciation Society. They have really beautiful photos of the variety of Earth clouds. I mean, they're not from space, obviously, if they're from your perspective, but it'll give you a much deeper insight into the variety of Earth clouds. And they have a really good set of explanations as to how they form. So you'll see, of course, that a lot of the work that we do is informed by our understanding of Earth clouds and vice versa, because these two systems, these two sets of atmospheres, they can inform one another and help us to understand both better. So if you want to start, this one is just for fun. You know, if you really like cloud spotting and you want to do more cloud spotting on Earth, you can learn all of these specific types, and that might help you as well here. Okay. I think this is where I was going to go. This is a cap in the southern hemisphere. You can see that, you know, if you were just glancing at this and you didn't know that the cap was down there, you might think that this was a really big disk cloud, or you might think that this was just generally cloudy. And so again, it really helps to sort of blink between the geometry. And you can see in this season, this is the southern hemisphere. By the way, this is a crater called Hellas. It's massive. This one here lets us know that we're in the southern hemisphere. If you've started to look at these images in detail, you'll notice that there is a strange discrepancy between the north and the south. And the south tends to have way more craters. You can kind of see that here. The southern hemisphere has lots more craters. And if I flick back to the northern hemisphere, it has a lot fewer craters. So that can kind of tell you ahead of time whether you're looking at the northern hemisphere or the southern hemisphere. But in this particular circumstance, even though we're looking near the southern cap, this is during a season when the cap, I guess, was not that extended. Whereas the image that you're looking at, it's huge, right? And so it's just nice to kind of look between these. And if you see like white near the poles, and you don't want to tag it as clouds, that's perfectly okay. It's okay to you know, leave that as something different that we can work on separately. Okay, let's show a couple more before we're running out of time and we don't have time for questions. So some features look like disk clouds, like this one here, but they're really just craters. So again, because of how deep the atmosphere is going, you have ozone that can literally pile into the bottom of this crater. And so you see that this crater is a little deep, and sure enough, ozone has just settled into it. And maybe at first glance, it looks circular and it looks like a disk. But that's kind of why we want to look between whether this is a cap, something that might be pure white, and whether it has any color like this. So these ones all here, these are all craters, and it's just ozone on top of them. Cool, there's the cap as well. Okay, this is another great example. So sometimes when you're using the higher resolution data, you can see stuff that looks like, oh, is this gravity waves? And you get really excited. And I told you we're going to come back to this image. This is really important that in the super high, in the higher resolution datas, you can see the surface. And there's all of these cracks that just live on the surface. And so when you look through the atmosphere, you're saying, oh, that's actually not in the cloud itself. That's just the ground, right? And so you might have something like this, which is certainly a cloud, but this dark and light is probably just a very uniform cloud, but you're looking down on dark and light on the ground, right? So here's the dark and light on the ground, and here it is represented as seen through the cloud. Whereas like something up here, as we flick over to the right, that same structure doesn't exist. So this is fully the result of clouds having a little bit of structure, right? So for example, if I looked over here and I said, is that a gravity wave? And then I look over here and it's not in the underlying geography, then I'd say, okay, then I'm going to tag that as a gravity wave because it looks like it has that type of structure as it goes across. Whereas this region is a little bit more complicated. Here's another example. Sometimes you have features that are way too big. So this thing up here, not a gravity wave in the sense that I traditionally think of them, but really cool. This is certainly clouds. So if I flick between the two, you'll see that there is no feature under here that is forming, it's not like this is the surface itself, but instead you still have this, this texture and this structure, which is not quite as regimented, but certainly looks like there is a cause for it, something that could be investigated. And this is a perfect example of clicking other. Just jump in there and be like, this is sort of weird. Is this covered by what we're talking about? And when we grab enough of these, we can kind of categorize them in one way or the other and see if we can turn that into, whether there's an Earth analog, something that we can compare it to understand the dynamics there, or whether this might even be a unique type of cloud that only exists at Mars. Okay. Okay, so this is, I think we've seen a lot of structures. Hopefully I haven't missed anything in my own slides. I want to tell you where we're headed because you're already doing such a great job getting through the data. So we are headed towards potentially something that looks like this. So not all of our data is of the highest resolution, but I think it's still very helpful. So this is what we call the medium or the low resolution data. This is our lowest resolution, but it's still quite good. There is another version of data that is super low, and I honestly don't think it's useful, so I doubt we'll ever see it. But we're going to experiment with this set and the one that I'm about to show you and see whether or not this is something that folks might be interested in digging into once you've gotten some familiarity, once you feel like you have a little bit of expertise in cloud spotting. You might be able to look at something like this and say, oh, I know exactly what that looks like. That looks like a curl, right? And that's the vortex cloud that we've been talking about. And you can still kind of see a lot of these features in here. So for example, that's a crater over here. This is the northern hemisphere, or sorry, the northern polar cap. So you can potentially feel like you're confident enough that even though these ones don't have as high a spatial resolution as we've been looking before, you might still feel quite confident going into there and trying to ID these clouds. So we're having some discussions about how we'd go about doing that once we get through all of the other types of data. There is something like 20,000 orbits of data that IVS, that the spacecraft has taken. We have currently gone through 1,000. So we're about 5% there. And I think, we're going to get through a lot more in the next couple weeks, next couple months. And eventually we'll be able to say, hey, we've built up some expertise. Can we start investigating this other type of data? So if you'd like to be included in that, let me know. Similarly, we might be looking at stuff that looks more like this. And you might say to yourself, that's completely useless. Most of it is not seeable. Well, this is, of course, the night side where you can't see because it's not illuminated. But on the day side here, this is actually past the terminator. So this is past sunset. And these structures might well be clouds. So what's really interesting is when you know how far a cloud is past the terminator, past the boundary of daytime and nighttime, if you can still see it illuminated, then you can kind of tell how tall it is. So this gives us some really unique information because we can get, for example, how wide they are, how tall they are. This can tell us a little bit about how clouds are forming as they go on to the night side of Mars. So these are two different experiments. I mean, this is obviously a little bit less fun to look at right away, but maybe if you're a seasoned veteran, you'd be like, oh, I can crush this in no time. And that might get you really excited as well. So our goals in the long term is that we're going to be using the subject sets that we've gotten so far. We're going to start grabbing sort of the what I would say is the most readily available scientific targets. So whether that is looking at where cap clouds form, whether that's looking at streaks in the data, we're going to use this in order to get out a publication, hopefully within the next year. And we then are going to sort of transition the result of that work and ask folks to do a new workflow on the similar. So let's say we've identified a cap cloud. Then we'll ask folks just to draw around it, and say, hey, cap clouds were identified here. Can you show me where the edges are? Because this will immediately give us some information on how wide they are, how extended they are. And that can really help the modelers to understand how big they need to make their clouds, how thick they need to make their clouds, et cetera. So if you want to become engaged in any of this process, you're also welcome to contact me and talk. I know that we have students. I know that we have undergrads who are maybe looking at this and saying, hey, I really want to get interested in Mars science for the first time. I'd love to chat with you about that and what opportunities might be available. And I want to just end by saying thank you. Of course, none of this would be possible without you. It's been really, really fun over the past 3 weeks getting to chat with a lot of you. And I continue to be blown away by your ability to spot things that, this is such a big data set that I think, oh, I've seen everything in it. But you're like, you're right there and challenging me to pay closer attention. So I hope that we'll continue to have these webinars every month. And I hope that you'd be interested in joining again. I thought that we would leave plenty of time to Q&A, but we kind of did it along the way. So if folks have questions, we'll stick around for some minutes and I'd be happy to answer them.
Yeah, maybe give it a minute or two for people to
Yeah,
form
yeah, no worries.
questions and type them, I think, right?
Oh, I see. I see. Yeah. Yeah, we're gonna save this presentation. I don't know exactly where we'll host it right now, but Merrick has a lot of familiarity. So if you're not already familiar, if you haven't seen Cloud Spotting on Mars, the original, that's a great project that is still ongoing, and I'm sure Merrick has a lot of experience with where these are hosted.
Yeah, I haven't typically uh, saved the presentation somewhere online. We uh, put all the recordings of the videos on YouTube, and you can access those there. But maybe there's one suggestion, and this is, yeah, something you can run with, Mateo, if you feel like it, is if you can release it publicly, put it on Zenodo or something, and we could even maybe do a small summary and link it in the blog that we have. And because the Zenodo isn't like a very fun site to poke around, but
Yeah.
if there's a little bit of text in a blog and a link to the slides directly, that might be one way to do it.
Yeah, we could certainly do that. We also, I mean, so for my classes, I always post them to YouTube. So maybe Cloud Spotting on Mars needs its own YouTube channel.
Yeah. And I think we could link or put a playlist with the other ones there too. It'd be great.
Yeah.
Um, a couple other questions. Oh, can you see these or do you want me to read them?
Yeah. I pulled up the chat now. So
Okay.
it looks like, yeah. So what happens if you make a mistake in identifying? Thankfully, we try to get enough volunteers on any one image such that we expect folks to make mistakes. I mean, everyone makes a mistake every once in a while. And even though, you're contributing to saying, hey, I think there's a cap cloud here, you might end up, say, clicking in the wrong place. And so we'll validate those ahead of time, so that we're not only taking exactly what we're seeing and then not looking at the results and comparing them to the images. So there's going to be a little bit of a data validation section. So I wouldn't worry too much if you made a mistake in identifying. Okay, let's see. There's another question here. Yeah, we could add a link from the field guide. Yeah, absolutely.
Yeah,
Uh,
and Ken had one about sort of possible could be yeah, what's the best way to handle those?
what I'm not 100% sure what that's in response to. Like
Uh
for,
kind of talking through the examples and it's like, oh,
oh
this one I'm
yeah,
not so sure, maybe it's this, maybe it's this.
yeah. So especially when you're thinking about whether it could be one object or another, right? So for example, we saw a lot of these examples where maybe you have a disk cloud and on top of it, you have gravity waves. So the first thing to do there, I think, is to identify the clouds. And once we have the disks, what the second part of this work is going to be is to see that we can grab all of the disks and try to outline where folks really think they are. So once we have sort of said, okay, this is where most people think the disks are, where is the edge, right? And that sort of leads to a second stage of validation in that process, as opposed to if we see something that maybe is considered other, or if one person marks, sort of a wispy type of thing, and they think maybe that's a vortex, but it turns out not to be a vortex, that's perfectly okay. That will not end up making it into the second stage. Does that make sense? Okay.
And
Yeah, go ahead.
yeah, Chris has a question. Part of it is about, yeah, sort of, you talked about a publication, kind of what do you envision for that? And maybe I'll take a stab at the second part of his question, which is, informing alien models or planetary protection. Uh, you know, uh, maybe people not so deep in the Mars research community aren't aware that like the wind, getting measurements of wind on Mars is really hard, but it's also really important. So, on Earth, we run these global climate models, weather models, and we have all these weather stations around which are measuring wind everywhere across the planet. And we basically have like one right now on Mars.
Yeah.
And so anytime you look at a model and you look at wind, you don't actually know if that's the true wind speed, and that drives uh, so much of climate and weather. And so yeah, I think especially with some of the wave structure you see there, if there's anything we can pull out for wind, the goal will just be to kind of pretty coarsely say what we think the wind speeds might be that are generating these, maybe look at some specific ones with a certain topographic feature and do some more detailed calculations about what the wind has to be over that feature to drive these. But I think that's all a little farther down the line. I'll let you speak more, but I would guess the first part of this is just going to be categorization and cataloging and kind of getting a bigger database about what forms where and what does it look like.
Exactly. Yeah. And I think especially to Merrick's point about like what can we tell when, it's this part of science is always a layered process. So we start by building a database and you hope that certain things will go into it and that you'll be able to understand X, Y, and Z from it. But I've already seen that folks are finding more stuff than we thought was possible. So for example, it's not so much that we just see one gravity wave and it's in an arbitrary direction, because that would be quite hard to compare with models. But what I've seen over and over is that people are asking similar questions about a specific feature with weird clouds coming off of it. And so when you start to see that over and over, you can say, okay, now this thing is persisting, and can a model reproduce this specific event off of this specific object? Because otherwise, it's not a very good model, right? Because this is a way sort of like, okay, at first you hope that you can just, okay, the model produces cap clouds or clouds over the volcanoes throughout this season. And that would be a great goal, if we could compare those two things. But if we can go a step further and say that the wind direction at this location is this for this long, then that's an even better way of doing that, right? So we start off with a goal, obviously, of the ones that we intended to find, and we've been really impressed by what we're finding so far. And I say we, and of course, it's all you guys, but
Yeah, there's a question in the Q&A too. Will the findings ultimately be made public or reviewable, and will any of the volunteers be listed as helping with the project?
Yeah. Particularly if you're interested in helping with the project, we'd love to have you aboard. We are going to acknowledge everyone in the acknowledgement sections, but if you want to help doing the writing, if you want to talk about Clyde ID, if you want to participate in the writing process, this is why I said that it was I'm happy to have you reach out. Part of doing science for groups as a whole is that I really want you to be able to feel like you're participating in science and you have agency in the scientific process. So if you want to reach out, we'd be more than happy to have you.
And coming to these webinars is probably a good start because, yeah, these projects are kind of always evolving. And it's things like this that, first it's, we're talking about the science motivation here. And pretty soon, I'm sure Mateo will be showing you kind of the first results, kind of trying to aggregate everybody's data. And that's kind of when the scientific analysis starts. So it's always possible these become less uh, top down from the scientist to you and more what's everybody seeing, what are some of the strange instances, and then maybe showing some writing that's been done so far and kind of try to build a paper. So um, uh, yeah, unfortunately, there's not usually like oh, this is the core team that's going to write the paper, but it's a little bit more organic and
Yeah.
yeah, so just keep in touch, uh, attend these webinars and tell us your ideas and see what happens. Yeah.
Yeah. So there's a lot of great comments about reaching out and whatnot. And I will just mention that I don't know if I did it in the last blast, but you should be able to find my contact information through Zooniverse, and you can write me a message directly there. You can also talk to Merrick. He's also a collaborator on this project, so you can reach out to him there as well. Part of the process is when we start getting data down, and in particular, when we start aggregating it from the work that you've done so far, we are actually going to post that right away, and we're going to have a Zoom webinar on that, where I'll sort of show you how to download the data if you want to look through it on your own. If you end up finding something that we've missed, or you want to, find do some exploration on your own, not on the pictures themselves, but on the results of the pictures, you're also welcome to do that. And of course, the writing process, while I'll try to guide it as best I can, there's a lot of steps that are more than just writing. So whether that is, creating an analysis pipeline, whether that means analyzing data in a specific fashion, this can all be a back and forth if you have a particular interest. That's the nice thing about open science, is that you get to do it as well. Thomas, this is a great question. We thought about using machine learning to help analyze all the images faster. And in fact, this kind of fits into a weird world of the machine learning, because everything is changing. So for example, the surfaces change quite frequently. The illumination angles change a lot. And I think by the time that you train the data set on a specific type of cloud, you may have run out, right? In order to like fully train that AI, you may have run out of data with then to validate it, because so many things are changing. And so, for example, we're seeing just a small subset of the data that's mostly head on. But as I alluded to in the webinar, some of it is seen more from the side or even from behind the planet, where that's going to look really different to the AI, and it will need more data to understand that. And then in addition to that, it turns out that I think in some ways, spotting these kind of random things, whether those are those wispy clouds or stuff that doesn't quite look like what we expected to, having a trained eye can in some ways be better because they can identify those things that are outside of the training set without needing new input, right? Oh yeah, Chris, this is a great question. So we are actually, the MAVEN spacecraft is still flying, and we take remote sensing data and we do it every 4.5 hours. So what my original plan was to upload new data every year. We may blow through that too quickly, so maybe it has to be every 6 months. But if we, as much as we can, we'd like to include additional data as it comes down. Okay, folks, if there's any more questions, we'd be happy to answer them either in the talk, or you can send an email to cloudspottingonmars@gmail.com. We'll try and figure out the next time for a webinar, I think in no longer than a month. But of course, we don't want it to overlap with Christmas too much. So maybe right before the holidays works best for people's schedule. If this time wasn't great for you, or if you are watching this after the point and you think that there's a better time during the day that can be more inclusive, let us know. And I know that, for example, if you're in Europe, maybe you weren't able to dial into this one. So give us some feedback in the talk. And if you want to send us emails about this, we'd be more than happy to hear from you.
Thanks for doing this, Mateo. Yeah, and thanks everyone for coming.
Thanks everyone for coming.